This is Calculus lesson number 12 in Tier 5, and it's going to be an overview of integral calculus. Now, as I've told you before, calculus consists of two fundamental concepts, derivative and integral. Now, as you know, we've already studied the derivative, or what is called differential calculus, and now we're going to take up the study of the integral, or what is called integral calculus. Now, the question is, what kind of problems is integral calculus going to be addressing? Well, the answer is we might call these what I would call accumulation problems. For example, what's the area of a two-dimensional object? Or what is the volume or the surface area of a three-dimensional object? Those are examples of accumulation problems. Now, our pre-calculus ancestors were able to calculate the areas and the volumes of some common geometric objects. And you learn about a lot of those in tiers 2, 3, and 4, circles and rectangles and things like that. But these studies were limited to some very special cases. Now, in STEM subjects, we must be able to calculate the areas and the volumes of a much broader class of objects. Now, for example, what would be the area under a parabola? Y equals x squared. And suppose you want to know the area from 1.2 out to 3.7. What would that area be? Now, Archimedes actually was able to figure this out, but it's not easy. It was a difficult assignment for him. The answer turns out to be 16.3 square units of area. You might ask yourself, how do you think you might be able to do that? Or take an ellipse. Here's an ellipse. 6 here, this is the major axis, and this is the minor axis. What would be the area of this ellipse? Now, it turns out it's 30 pi. In fact, you can see that's 5 times 6 times pi. But the question is, how would you figure that out? How would you know that? How could you actually do that? And of course, that is the kind of thing that we're going to be able to easily answer using calculus. Or suppose you wanted to know the area underneath a circle bound by two vertical lines intersecting the diameter from some point here to some point here. I chose minus 4.5 up to 6.7. What would this area be? Well, it turns out that it's 89.2 square units, but how would you figure that out? It turns out, of course, it's very easy to do with calculus. Another example would be, what about the area under the sine curve from 0 to pi? Well, it turns out it's 2 square units, but again, how would you figure that out? This would be quite challenging, and indeed, our pre-calculus ancestors would have had a very difficult time in solving either one of these problems if they could have done it at all. But it's very easy to do with calculus. Now, another example would be to take a parabola, y equals the square root of x, and rotate it about the x-axis, and you create what is called a paraboloid. In fact, this is how many dish receivers are made today, both for receiving radio signals or sound signals. Well, the question would be, what would be the volume of this paraboloid, and what would be its surface area? Now, that's quite difficult to calculate using any classical techniques, but with calculus it's very easy. It turns out if you're going from 0 to 2 here, and this is the paraboloid, the volume is 6.3 cubic units, and the area is 14.6 square units. You can use any units you want, inches, feet, whatever you want to for linear units. And volume is always cubic, and area is always square units. Or what about the arc length of a curve? Here again, I've taken the parabola, y equals the square root of x, and how long would this be, the arc length of this? It turns out it's 4.65 units, which you can find out easily with calculus. And there's no other easy way that I know to do it other than to use calculus. And this was example number 5. Okay, now all of these examples and many more examples that are even more complicated than these are easily solved with integral calculus. And of course the question is how? Well, an irony is that one key to their solution is to use what are called antiderivatives. And of course you can get antiderivatives essentially from derivatives. It's working backwards. Now, this is what our ancestors discovered. They discovered this in the 1600s, and so they've been using this for over 300 years. And in fact, this discovery they made is what is today called the fundamental theorem of calculus. Arguably the most important theorem in the history of mathematics, because you can certainly argue that all of our modern technology, and indeed our science and engineering and STEM, grew out of this discovery. This discovery was made by Newton and Leibniz, and some of their contemporaries worked with them, and then it was really developed in the 1700s extensively by great mathematicians like Euler. And in fact, it really is what revolutionized the way we do science, the way we can do engineering, and the way we can develop our technologies. Now, one of the reasons this fundamental theorem of calculus was so important is that it reduced the numerical calculations you had to do tremendously. You could have solved all these problems with ordinary arithmetic if you had a limited amount of time, but this reduced it by orders of magnitude. Well, then it turns out that all this changed with the invention of the computer. Now, if you've got access to computer, you can get very accurate estimates to all of these types of questions just by brute force arithmetic calculations using a computer. Now, ironically today, if you have a tool like Wolfram Alpha, you can actually solve these problems both ways, as you're going to learn. You can solve them by using the fundamental theorem and antiderivatives the way our ancestors did very easily and quickly now compared to the way they did it, but you can also do it with brute force if necessary, and many problems have to be done with brute force. And you can do this either way when you have a tool like Wolfram Alpha. Now, what we're going to do in this course is, first of all, you're going to learn the definition of integral in a very precise way from a geometric viewpoint that makes it very easy to understand what it is. And then second, you're going to learn what the fundamental theorem of calculus is and how to use it. You're going to be able to use it like our ancestors did whenever they evaluated these types of problems. And as a matter of fact, it's a wonderful, beautiful theorem to see, and it, in a certain sense, is very easy to use, and in another sense, it's quite difficult to use. And then the facts are, you'll be able to use Wolfram Alpha along with the fundamental theorem to evaluate any integral problem you need to. In fact, it's just truly amazing how you can do this with Wolfram Alpha, and you can combine the best of what our ancestors did and what we can do now with modern technology. As a matter of fact, our ancestors couldn't solve a lot of problems even with the fundamental theorem. They just simply were not able to. But with Wolfram Alpha and the brute force techniques that computers apply to it, you're going to be able to solve problems our ancestors couldn't even deal with. As a matter of fact, problems that would be impractical to do manually with calculus or even with a calculator. And Wolfram Alpha will do that for us. So the conclusion we have is that today, I say it's pretty easy, I probably should say very easy, to learn the basic calculus concepts and also how to use a tool like Wolfram Alpha to solve virtually any calculus problem very quickly and very easily. Now, there are many applications of integrals in virtually all subjects in science and engineering, so-called STEM subjects, and in fact in any other quantitative field. In fact, if you go into any kind of a STEM field, you're going to be finding examples in a never-ending way. There's really just an unlimited number of examples you'll run into in all sorts of science and engineering. Now, as a matter of fact, many of the integral calculus tools that our ancestors developed and used are now effectively obsolete in that no employer is going to pay you to use these old manual tools to solve a calculus problem. As a matter of fact, it was quite difficult to use these manual tools. Techniques of integration is the subject that probably flunked more kids out of technical schools than any other subject that I know of. Many students that wanted to study science and engineering and other STEM subjects simply couldn't get through the techniques of integration course in calculus. Now, that's no longer the case. Wolfram Alpha is going to enable you now to use these techniques very, very quickly and easily. Now, unfortunately, these tools, these manual tools, are still often taught in typical calculus courses and covered in typical calculus textbooks. And you certainly can learn them if you like. We're going to show you what they are. But the facts of the matter are, you're going to find Wolfram Alpha is much easier to use. And if you do learn these manual techniques for whatever your reason, you can always check your work very quickly and easily with Wolfram Alpha. Now, a modern calculus textbook can be a good source of problems and applications of both differential and integral calculus. And you can certainly solve these problems with the classical manual techniques that are usually taught in these books. But you can also just use Wolfram Alpha if you want to. And even if you do decide to learn to solve these problems with the classical techniques for whatever your reason, you can always use Wolfram Alpha to check it out. And in fact, it's imperative that you learn to use a tool like Wolfram Alpha, since this is really the way that any modern STEM professional is going to do calculus type problems. I might also add that in these calculus textbooks, some of them today do use graphical calculators, and that's an improvement over the pre-graphical calculator books, but it's still a long way from having a powerful tool like Wolfram Alpha. Wolfram Alpha is much, much more powerful than any graphing calculator. After all, when you use Wolfram Alpha, you're going to be using a whole bank of computers with extremely powerful software. It's an online program. In fact, Wolfram Alpha is going to make the application of calculus probably 90% easier than it was with the old classical approach. It's just amazing how quick and easy it is today to solve calculus problems with Wolfram Alpha. And it also makes it then much easier to understand the concepts of calculus and their applications, because after all, you really learn the concepts by doing lots of problems, and when you can do them easily and quickly, and when you can apply it to a lot more things, then you learn the concepts even better. In fact, what you're going to be able to do now is to take other types of science and engineering books in all sorts of fields and go in and study them, and when they start using calculus to do their things, you're going to be able to do it very easily with Wolfram Alpha. So you'll no longer have to be intimidated when you study physics or electronics or hydraulics or mechanical power systems or any technical subject, any science book, by the math in it, because most of the math they're going to use is calculus and differential equations, which will be an extension of calculus. You'll get in Tier 6, and you're going to be able to solve these problems now very quickly and easily with Wolfram Alpha. It's going to transform how you study STEM subjects. And so I encourage you now to move forward. You're going to find that this next part we're getting ready to do on integral calculus is no more difficult than what we did with differential calculus. Thanks to Wolfram Alpha, that didn't used to be true in the old classical way at all. And you're going to be able now to learn this very quickly and easily, and soon you'll be then ready to go out and tackle all sorts of STEM subjects where you're going to get really all the examples you'll ever need for these techniques. So I'm looking forward to having you as a student in this upcoming lessons in calculus. I'll be your tutor on the videos, as you know. And of course, I'll be your coach in the forums, as we have been in the past training you've been taking. And you're going to have a really good time in learning these subjects. It's going to be a lot of fun. It's going to be easy, and it's going to open up tremendous vistas for you and opportunities for your STEM future. So Dr. Dale, wishing you the very, very best moving forward.